Okay, so we're gonna discuss some issues about failure prevention from static loading. Okay, from static loading, but maybe not just from static, also cyclic loading. I will uh, introduce this cyclic loading failure later. Okay, so look at this kind of a component which is a track draft shaft spine. Okay, so it broken or it failed due to the corrosion fatigue. Okay, so maybe this track is drive around high humid environment every day. Okay, and this driver never could take good care of, a truck. Okay, I mean he might not keep maintaining or repairing its truck every maybe 3 months or 4 months. Okay, it totally depends on how frequently you use your devices and how is this condition. I mean, this circumstances of your components or the environment of your component will severely influences your the failure of your components. Okay. Also, and this low mower blade driver hub. It was broken by a surveying pipe maker. Okay, so maybe something hit this stress concentration area. Okay, to to broke it down quickly. Okay, and it's the boat for some weightlifting machine. Okay, so obviously it was broken due to the bending, right? So this boat might be subjected to most of the weight, okay? Most of the weight from bending. And also, there are different type of failure, like this is a spring, right? This is spring, valve spring failure caused by a spring surge in the oversped engine. Okay, so maybe the piston move back and forth, okay, with high speed. And the fractures expected class 45-degree shear failure. Okay, so as what I mentioned previously, most of the metal failure, I mean, the slip will occur in the closed pack plane, right? And it's closed pack plane with the specific angle 45 degree. Okay. Okay, so let's focus on the failure theory. So the first we have to divide it into two materials. One is brittle and ductile. Okay, we're gonna utilize the different failure criteria. Okay, for the brittle, what the criteria, what the failure theory we're gonna use. First is the maximum normal stress and the brittle coolant more and the modify more. Okay, and for the ductile material, what is the failure criteria we're gonna use? There's a yield criteria, right? And it's based on the maximum shear stress, distortion energy method, and the ductile coolant more. Okay, so now I'm gonna just focus on the brittle behavior first. Okay, okay. So how to define the safety vector, which can be defined as the allowable stress divided by the current stress, or we say the allowable shear stress divided by the current shear stress, right? So when we apply a tensile test to a brittle or a ductile materials, what kind of this stress and strain curve it should be? So for the brittle material, right? So there's no yielding occurs, right? No yielding occur. So the relation between the stress and strain curve, mostly will be linear or without any plastic deformation, right? So so we can regard this relation between the stress and strain. Mostly it's the linear, okay? And of course for compression is also linear. Okay. Okay. So the fracture strength of the brittle material is the maximum tensile strength, which is different from the ductile material. Why? Because when we apply a tensile to ductile materials, right? So we are going to find the ultimate tensile stress, okay, the UTS, right? And then we can define its yielding stress, sigma y, right? However, for brittle, we cannot find this ultimate tensile stress and the yielding stress, right? Therefore, we define the maximum tensile stress, which is the fracture stress, okay, or the maximum compressive stress, okay? As you see, it's defined as the maximum compressive stress, okay? So usually the compressive stress is higher than that of the tensile stress. Okay. So both of them are the materials properties. So you can check any the materials book or handbook. For example, for cast iron, whose ultimate tensile stress is 30 ksi, and whose the ultimate compressive stress is 110 ksi, almost 3 times higher, right? Almost 3 times higher. Okay. Okay. So for the principal stress, So you guys must be familiar with Mohr circle, right? So let's discuss with different cases of the Mohr circle or of the principal stress. Okay, so here I use the notation sigma A and sigma B as the principal stress. Okay, and later on I'm gonna change it to sigma 1, sigma 2, and sigma 3. Okay. Okay, so for case 1, what's the situation of the case 1? What's the situation of the principal stresses of case 1? I mean, the sigma A and sigma B are both negative, right? Are both negative. Okay, so what is the case 2? It means the sigma A and sigma B are with the opposite sign, right? And for the case 3, the sigma A and sigma B are both positive. Okay, are both positive. Okay. And remember one thing for the brittle materials, the ultimate tensile stress equals to the maximum tensile stress, and the ultimate compressive stress equals to the maximum compressive stress. Okay, as SUT and SUC. And usually the compressive stress is maybe much higher than the tensile stress. Okay. Okay. So for the brittle materials whose failure criteria, the first criteria is called the maximum normal stress. Okay. So as what I mentioned previously, the sigma A and B are the principal stresses, right? They have to be smaller than the ultimate tensile stress, right? The same, the sigma AB, whose absolute value have to be smaller than the ultimate compressive stress, right? So we define the factor of safety, or the safety vector N equals to the SUT, the ultimate tensile stress, divided by the sigma A or sigma B. Depends on which stress is higher. Okay, depends on which stress is higher. Okay, or we can define the ultimate, the safety vector equals to the ultimate compressive stress divided by the absolute value of the sigma A or sigma B. Okay, depends on which value is higher. Okay, so now we can draw a stress envelope of maximum principal stress. Okay, we can draw a stress envelope of maximum normal stress. So first we can find it's the ultimate tensile stress, right? For the specific materials, we'll just check the table or you can Google it, right? And the ultimate compressive stress, right? Then we get 4 point, we can draw a square, right? We can draw a square, okay? So the x-axis represents the sigma A and the sigma y, the y-axis represents the sigma B, okay? So these two axes represents the principal stresses, okay, principal stresses. Okay, so in the three area, 1, 2, 3, shows that the sigma B is greater than sigma A. Okay, sigma B is greater than sigma A. Okay. Okay, so let's look at different stress condition within this stress envelope. Okay, for example, in the first quadrant, right here, in this case, we can assume the sigma A is greater than sigma B, right? Sigma A is greater than sigma B. Okay, no matter what, I mean, we just assume that the stress condition is located at the first quadrant of the stress envelope. And then we can define its safety vector equals to SUT divided by sigma A, because the sigma A is higher than sigma B. Obviously, if the sigma B is higher, we just use the sigma B as the denominator, right? Okay, so for the case that the stress condition is located at the third quadrant, okay, so in this case, the absolute value of the sigma A is greater than the sigma B, right? Because it's within the third quadrant, that's mean within this compressive area, okay, compressive area. Therefore, we can define a safety vector equals to SUC, the ultimate compressive stress divided by the sigma A value, absolute value of sigma A. Okay, and in the same quadrant, if the sigma B is greater than sigma A, okay, we just change the sigma A to sigma B. Okay, it totally depends on which absolute value is higher. Okay. Okay. Okay, so if this stress condition is located at the second quadrant, and the sigma A is minus, the sigma B is plus, right? It's positive. Okay, so we can define its the safety vector. Suppose we define the safety vector as the N1 equals to the SUC, right? Because it's in the compressive and the tensile area, right? So this point is for the compressive and this point is for the tensile, right? So we use the SUC divided by the absolute value of the sigma A, we get the N1. And we can also use the SUT, the ultimate tensile stress divided by the absolute value of the sigma B. We got the number stress vector N2. Okay, so what's the difference between this N1 and N2? So from this stress envelope, we can evaluate the safety factor of N1, which is close to 1. Okay, and this safety factor N2 is close to 2. Why? Why? Okay, for N1, right? For N1, the denominator is SUC, right? It's this distance divided by sigma A, right? So you can see these two, if we just the two lengths of SUC and the sigma A, right? And then we just divided SSUC divided by the sigma A. Well, from the length point of view, wow, it's almost the same, right? It's almost the same. So we can say, well, the safety factor, well, it's close to 1, yeah, 1.1 or 1.01, like that. Okay. Okay. So the same thing if we just look into the tensor test, right? This SSUT distance, right? And if for the sigma B at the second quadrant, it's this distance, right? Therefore, the SSUT divided by sigma B, well, it looks like 2 or higher than 2. You know what I'm saying? I mean, we just evaluate from the stress envelope, okay? From the stress envelope. Okay, so the second failure criteria for brittle is called the Coulomb-Moore. Okay, Coulomb-Moore. So let's look into the infinitesimal element with the sigma A and sigma B, which is the principal stresses, right? Therefore, we can draw the Moore circle, sigma A and sigma B and sigma A. Okay, suppose we already know the value of sigma B equals to 29 KSI. And for these materials whose ultimate tensile stress is 30 KSI. Okay. Therefore, we can draw the Moore circle. We can draw the Moore circle, right? Of the sigma A and sigma B right here, right? And the SUT is 30 KSI right here, right? And it's SSUC right here, right? If we know the materials, we can just check its materials property, right? Okay. Okay, so in this case, we can draw the Moore circle with the ultimate tensile stress and the ultimate compressive stress, right? And if it's a plane stress, that means in z direction equals to 0, right, at this point. Okay, therefore we can draw the two Moore circle, right? This one, the green and the blue one, this one and this one, these two, right? And the red circle represents the Moore circle of this element, Okay, so we have three circles, right? 1, 2, and 3. And the third circles, the red circles, represents the stress situation of this element. And the circle 1, circle 2 represents the ultimate tensile stress and ultimate compressive stress. and using them to draw the Mohr circle with the plane stress. Okay, and then we can connect, we can make the tangent line, right? For these two circle, blue and the green. Okay. So any stress condition, right, is the sigma, and it's the shear stress within this area should be safe, right? Right? So in this case, this area, safe area should be here, right? Because the red circle represents the stress condition of this element, right? Of this element. Okay. Okay. So what is the Coulomb-Mohr? What's the Coulomb-Mohr? Last slide, we just draw the Mohr circle, right? So now we're gonna plot this stress envelope of the Coulomb-Mohr failure criteria. Okay, so the difference that we just connect this compressive stress to the ultimate tensile stress, right? For the maximum normal, whose stress envelope is like this, right? However, for Coulomb-Mohr, right, we just connect SUC connect to the SUT, right? So if the stress condition is located at the first and third quadrant, whose safety vector is the same as that of the maximum normal stress, right? Okay, so the things that if the stress condition is like in the second and the fourth quadrant, so what's the safety vector should be? What the safety vector should be? Okay, so the second quadrant, right? Second, right here. Sorry, it's not quite correct. The second quadrant. So for this linear line, we can just use the linear equation as y equals to mx plus b, right? M is the slope, b is the y-intercept. So in this case, the slope equals to SUT divided by SUC, right? So this slope, n, right? And the b equals to the SUT, right? B is right here, right? So we can plug this number here, plug this number here, right? So we get the sigma b value is smaller, should be equal. Let's just change the equal to the less than the SSUT divided by SUT times the sigma a plus the SUT. Okay, and then we just times the we just divided by the SU. We just make some rearrangement of this equation, right? We can tie the SSUC on both sides, and you just rearrange this equation. We'll get this final term of the Coulomb-Mohr criteria. Okay, and then we define the the uh, the safety vector equals to, okay. Okay, the similar process if the stress condition lies in the fourth quadrant, so right now we have to find the linear equation, right? In the fourth quadrant, the same thing, we're gonna find the slope and the intercept, right? Okay, so I just skip those process because it's almost it's the same process. I'm not gonna repeat this problem. Okay, this process. So basically, we just exchange the sigma A or sigma B. So here in the second quadrant, which is sigma B, and in the fourth quadrant, we just change to sigma A. Okay, and in the second quadrant, here is the sigma A, and in the first quadrant, we just change to sigma B. That's it. Well, you can just play with those maths by yourself. Okay, it's not difficult. Okay. Okay, and the third failure criteria is for brittle. Okay, and the third criteria is the most close to the experimental result combining of the previous two criteria. Okay, so we define the ultimate tensile stress and ultimate compressive stress and ultimate tensile stress and ultimate compressive stress. And then we plot a hexagonal shape. We plot a hexagonal shape. Okay, so in the first and the third quadrant, they are the same as the previous two, right? The difference is the stress condition located at the second and the fourth, right? For the previous one, the Coulomb more, right? So we just connect these connected, right? Right. So we find this linear relation, right? Okay. However, here we can just use the linear equation of the Coulomb mole, okay? The Coulomb mole, and we also similarly we have to find the linear equation of the modified mole. Okay, modified mole. Okay, so we have to find this linear equation. Of course, then simply the linear equation, we can assume it's y equals to mx plus b, right? And for here, the slope is different. A equals to the SUT divided by the SUC minus SUT, right? The slope, right? And the intercept, the y-intercept is B right here, right? Y-intercept, we can plug in Y in M here, and then you can find the B value. Okay, we can find the B value. And the B value equals to SUT plus SUT divided by SUC minus SUT times SUT, right? Okay. And now we can just plug in this M and B into this linear equation, right? M value right here. Plug into M, right? And the B value. Let's plug into this B here. And Y equals to sigma B. Okay, Y equals to sigma B. Okay, so we get the equation of the modified Coulomb-Moore equation, and we just make a rearrangement of it. Okay, finally. Okay, finally we get this relation. Okay. Okay. And for this linear function in the first quadrant, you can just derive by yourself. I mean, it's almost the same process. Okay, it's almost the same process. Okay, so finally we got the equation for the Coulomb-Moore, and we define the safety vector, okay, by using the Coulomb-Moore, okay, by using the Coulomb-Moore. And this relation especially has to be used in the second and the fourth quadrant, okay, by modifying Coulomb-Moore criteria. Okay. Okay, so we can just plot the three criteria, the stress envelopes of the three criteria in the single picture. Okay. Okay, so the first we have the maximum normal, right? And then we have the Coulomb-Moore. And finally, we learn how to plot the stress envelope of the modified Moore. Okay, modify Moore. Okay, so this is one example here. Suppose we have the bar with the L shape, right? We apply a force and this end is fixed. So can you evaluate or can you just figure out what kind of the stress applied to the point A right here and the point B? Okay, point A right here and the point B. So let's focus on the fracture criteria for the brittle materials. Okay. So let's do some force movement. Okay, let's do some force movement. So the force P can move right from this position to here, right? So when we move the force, which is not along its reaction line, there must be a moment, right? Okay, so let's focus on the point A. That's infinitesimal element A. Okay, so the force P will produce the bending stress, right? Will produce the bending stress to the point A, right? And the moment M, which is a torque, right? Produce the torsional stress to point A, okay, to point A, right? Okay, so for the point B, the moment which is act as the torsion, a torque, right? Therefore, for point B, it will feel as the torsional stress, right? And it's the maximum torsional stress, right? And the force P, right, acts at point B, which will produce the transverse shear, okay? Transverse shear stress. Okay, so maybe you firstly you don't have to know how to calculate it because the computer can help you to do those math work. However, in your mind, you have to know to realize what this point A, what kind of stress applied to it. Okay, it's the most important things for machine design because well the computational things we can just turn into the computer. However, if your concept of the stress is wrong, your design is a catastrophic disaster. Okay, because you have to know what kind of the stress is the key vector to cause failure, right? So you have to imagine what kind of the stress applied to point A or point B, or I can say, okay, some point right here, inside here, some point inside right here, right? Okay, you know what I'm saying? Okay. Okay, so let's look at the other example. Suppose we have the element which is the cast iron subjected to the compressive stress, normal stress, compressive stress, and the shear stress. And for this, the sigma x equals to minus 60 compressive, right? And sigma y equals to minus 40. And the tau xy, the shear, equals to 35 ksi. That's we already know. And then we can figure out what is the average stress, which is the center of Morse circle. Okay, which is the center of Morse circle equals to minus 50 ksi. And R represents the radius of Morse circle, right? Radius of the Morse circle. Okay, so we can find it's the radius. So when we already found the center and the radius, and then we can draw a circle, right? We can draw a circle. Okay, so the average stress, the center right here, right? And the radius, right? The R. Therefore, we can find the sigma A and sigma B, the maximum normal stress equals to minus 86.4, and sigma B equals to the 13.6 KSI, right? Therefore, we get the sigma A here, right? Sigma A and sigma B here, right? Well, I think it's not quite difficult, right? Okay, so for the cast iron, whose ultimate tensile stress is 30 KSI and its ultimate compressive stress is 110 KSI. Okay, so we can draw the stress envelope, right? We can draw the stress envelope. We know the ultimate SUT is 30 KSI, right? And SUC is 110, and the 30 KSI, right? And we already calculate its principal stresses. Y is minus 86.4. Sigma B is the minus 13.6, right? Therefore, the stress condition is lies in located at the third quadrant right here, right? And what's its safety vector? Or the safety vector is, okay, from the maximum normal stress criteria, right? The safety vector equals to which one's higher? Which absolute value is higher? I mean, which absolute value of the principal stress is higher? Compressive, right? It's 86, much higher than 13 something, right? So we know the compressive stress, sigma A, is the higher value. Therefore, the safety vector equals to the 110, which is the ultimate compressive stress divided by sigma A, and whose safety vector equals to 1.273. Okay, so this is an example to use the to use the maximum normal stress. Okay, and the second example, is like this. The same, we have the element, right, with the tensile, compressive, and the shear stress. So the sigma x is minus 18y, sigma y is 12, and tau xy equals to 8 ksi. So the center of Mohr circle is minus 3, and the radius of the Mohr circle is 17, right? And then we can figure out what is this, the principal stresses is. Okay, so right now we can use the 3 criteria to figure out the safety vector. So we just plug the 3 criteria into one stress envelope, right? Like this. So the sigma A is minus 20 right here, and the sigma B is 14 right here. So the stress condition will locate at the second, right? The second quadrant of the stress envelope right here. So if we use the maximum normal stress, what its safety vector should be is equals to the ultimate tensile stress divided by sigma B, right? So the 30 divided by 14. So we get the safety vector equals to 2.14. Okay, and if we use the Coulomb-Mohr criteria, right? You still remember this relation, right? So we can just figure out this value equals to 0.68, 0.648, right? And its safety vector equals to the 1.542. Okay, and for the modify Mohr, right? Modify Mohr, we can plug those number, the SUC, SUT, and sigma B and sigma A, right, in the Coulomb-Mohr equation. Okay, so finally we get its safety vector equals to 1.9, 1.92. Okay, so one is 2.14, 1.54, and 1.92. So which one is the most conservative criteria? The first one, right? The maximum normal stress, because its safety vector is the highest volume. Okay, it's the highest volume. That means we're gonna use more materials to to fabricate or to manufacture those components. Okay, so from the graphic point of view, we already know the stress condition right here, right? Right here. So if we draw the straight line from the center, from the origin, we draw the straight line. This straight line, we have the intercept with this this modify Mohr at stress envelope and the Coulomb-Mohr stress envelope, right? So if we use the modify Mohr criteria from the graphic point of view, we just find the ratio between this length divided by this length. You will get the safety vector. Okay, you get the safety vector. Okay, the same thing if we let's change the color. Okay, if we use this length divided by this length, we'll get the safety vector by using Coulomb-Mohr criteria. Okay, and if this, we call this a line, the loading line, if this line is rotated clockwise, right? So we have the new loading line right here. So what's that mean? That means safety vector will change. Will change higher or lower? Will change higher or lower? Lower, right? Or change lower to lower safety vector. Okay. Because this ratio to this ratio is higher than, should be higher than this ratio to this ratio. Okay. So also you can think of if this loading line become more. So we're gonna have the intercept, right here. And what's their safety vector should be. Okay, so you can think of it. Okay? It's not difficult. It's just from this it's a graphic solution. Okay, and you can use the graphic solution compared to the calculation. Okay, the calculation. Okay, it should be the same result of the safety vector Okay. Okay, so we're gonna stop the course here, and for next course we're gonna uh, focus on the ductile materials, right? So previously we just focused on the brittle. And for the next course, we're gonna introduce what is the failure theory for ductile, okay, for ductile material, okay, for ductile materials.